So you're going to be using this software. I've recommended this because it's easy, it works well, and it's not really that much painful to work with the software overall. And it works both with meshes. It actually accepts that mesh, and it works well with point clouds too. Um, so in your final project, what you have is essentially you have a nice model that you have to import into this. The model is an FBX format. Each group has a particular place of the sites that I put together. Some of it I basically make it a bit large or smaller, but it doesn't matter. Then you have to superimpose your point cloud on top of that and utilize some method in order to find whether a particular element is in a particular location or not. And the problem is that we don't have really software that does that in a let's say open source manner. So I'm going to teach you how to use that and circumvent that situation. And hopefully later on in your companies, you would be able to implement what you've learned here and even grow a bit more and even maybe use and develop more algorithms that can benefit this process together. So the first part is I wanted to show you the user interface overall. So you have basically a file similar, you can open it, you can close, you can quit. In the edits, you have multiple different aspects. Normals means normal vector of basically either a set of set of points or set of other aspects. You have the opportunities with registration, which we're going to talk about. Actually, CloudCompare is quite prominent in the ability to do registration. You have segmentation, extracting, they're fitting, and then you can change camera positions with the display. You have the plugins, and these plugins are basically open source software that exists. So for instance, RANSAC is a famous shape detection. It's called, it stands for Random Sample and Consensus. And I'm going to talk about this a bit in our courses too. And CloudCompare actually uses a few random sample and consensus type shape detection methods that are quite established in academia. I personally, in your paper that I've written, I actually showed that the basically the RANSAC method here does not really work that well, especially if you have multiple types of objects that you're detecting from. And there is quite a bit of type 1 and type 2 errors associated with that. So in one of your assignments, you're actually supposed to use the random sample and consensus here in order to detect pipes. And then there you're going to play around a bit with the thresholds, and then you're going to understand that these thresholds are actually not quite accurately identified. And these methods are quite reliant on the accurate threshold, which that accurate threshold again comes back to the accuracies that you're expecting from that particular device. And it's quite surprising that it took until 2021 that I published a paper to actually talk about this. I have don't have a recollection of another academic actually talk about how important it is to see what the original data was and how it impacts all of the thresholds that you might have throughout your detection. And this is going to be one of your assignments. I believe it's assignment number 4, if I'm not mistaken, and that's the pipe detection. And I've given you some images to perform that as well. So you have some functions here with the plugins, and you have other aspects there. So this is more or less how it would look like when you open it up and you see how it is. There's some other functions here as well. I strongly recommend you to take a look at it, maybe play around with it a bit more, see how it is, see what does what, and then from that kind of have a bit more idea. It's an open source software, so the beauty of this is later on you might be able to even add additional APIs to it. So this is something that I have done before myself as well when I wanted to streamline a particular process. And also, I'm not a brilliant programmer. I don't come from a computer science or computer engineering background. So As long as the logic is there, you can still utilize that within a good graphical interface here, and then have a good program at the end. So the first part that I want to talk to you about is opening the FBX format file, which I basically had this BIM that I created. It's a very crude, very low-level BIM. However, it does the job. I've actually shown you how it looks. And this is, for instance, the first epoch of overall. But in your projects, you're going to see that this is divided quite a bit, mostly because I didn't want you to focus too much on the computation time, but on the concepts itself. And if you take a look at it and see how it is, you're going to observe that it's been represented here by what it is. It's a concrete rectangular column. This is the size of it, and so on and so forth, what the vertices are. And you have some information of, for instance, if you have a triangulation, which this is how it actually saves the mesh, meaning every surface that is rectangular would be divided almost in two surfaces. So, for instance, for a cube or a rectangular prism that we have here, you're going to have expectation that you're going to have 1, 2, 3, 4 surfaces that are surrounding, and then 1 or 2 top, which is going to be 6 surfaces, and then twice as much as that, so it's going to be 12 triangles that you're going to see. And some of it you're going to see a bit more based on how that is. It might not be a full rectangle, or it might change in a particular area, so it adds a bit more triangles there. But for the most part, that's how it is. So this is the mesh. What you need to do here is to make this mesh and this is the pre-processing that we're going to talk about later on in our course, where I would like you to play around with it a bit more as well, and then see how you can save it in, let's say, a text file, where a particular column, you can understand what's the boundaries of a particular facet is going to be, and what's the normal vector of that is, what's the other attributes of that is, what the projection of that is, because a surface would be represented, a planar surface would be represented by its normal vector and the projection distance. So, and of course, the boundaries of it as well. It would be good to play around, see how it is, or to see how you can actually make this into a bunch of points. There's a tool there. I like you to kind of play around with it. I'm going to explain it later on as well. Because what you need to do is you need to then superimpose the point cloud on this, and then elements by elements for the BIM, see what points are around it, and then basically register those points onto this element, and then see whether it complies with the standards that you, or the minimum tolerance requirements that you think, or how much that tolerance is going to be, and whether you can find the particular elements there in the vicinity or not. And that is also very important. So the next part is to open up your point cloud. Oh, this is, I think, this part. I think this is, yeah, okay. So this part is to scale the model. So sometimes, especially with CloudCompare, what ends up happening, if you take a look at this, it's called scale to centimeter, meaning that when it actually uploaded it inside, you have some sort of scaling mechanism there that exists. This is mostly because, for instance, you have your BIM in either, let's say, inches. When you're converting it, it's not as interoperable, even sometimes if you do it properly. But this basically shows that, and this shows very exactly that it was in inches, but it's really in meters that you're supposed to do that. So you need to rescale this in order to be able to see a proper comparison between what reality would be. And this is basically where you're going to use that scale in your example. So you're going to use this scale, basically 1 over this scale, or basically this is scale to centimeter, you want to have scale to meter. So how you need to utilize that is by selecting all of it, by going to edit, and by selecting the multiply scale. So scale to centimeter was 30.48. Scale to meter would be 0.3048. So you basically use that there. This means that now the model that has been imported is going to have a scale that is 1 meter represents 1 meter. Because if you don't do this and you put your point cloud there, you're going to see that your model is quite bigger than your point cloud and exactly as much as this scale. So this is the first part that you need to perform when you're actually uploading the model there. The second part there is, for instance, here I'm uploading the point cloud. So you're going to see here that you have a few columns. You have your X coordinate, your Y coordinate, your Z coordinate, and your scalar. The scalar, as I mentioned before, it's basically your intensity. How hard a particular laser beam is going to reflect off of a particular surface. That's what you see, and the color that you're going to see basically represents that. And the first part is the number of points. Now, I've given you a MATLAB code to be able to read this whole beautiful file that you see here. It's which is in .pts format, which basically takes a look at this, and then from that basically reads the rest of it, gets the 3D coordinates and gets the scalar there. And the reason why I did that is because I didn't want you to focus too much on, let's say, how do I even read this through that, but focus more on the logical aspects of what needs to be performed later on, because no, it's good for you to know how to perform the programming overall. But for me, it's more important for you to understand the concepts, because later on, as construction managers, as leaders of a particular area, you can know what needs to be performed more so than what needs to be done in the sense of the nitty-gritties of the programming. So this is basically it. You're going to take a look at that. You don't need to necessarily change too much of that. Let me put this again here. So, oh, I think it was here. Yes. So here, what you do is you can skip one line. And basically when you put here, that one line that is going to be used, which is the number of points there, you would be able to remove that one line. My program actually uses that, so you don't need to resave or anything like that. If you want to open your PTS format in MATLAB, the only thing that you need to do is you need to save that particular function that I've put there in your project, in wherever your MATLAB is in that particular area. And then you need basically that particular epoch that you want to open up. And then you basically put that function there, which I'm going to explain, and it would read the whole file. But in this, it's a good practice to remove that. If you don't remove it, it would still read it. There's no problem. But it's good for you to know that you can have that flexibility if you really choose to. And then basically it's going to read that. This is going to be a bit more than I believe your portions, because you're going to be portioned here. And this is a highly reduced point cloud as well. This is a terrestrial laser scanner point cloud, but this is mostly, again, for demonstration purposes that I wanted you to get familiarized with this. And then you have a few other aspects. So if you go and zoom in, you can actually click on a particular point and it would give you the scalar field, which is the intensity, and then the XYZ coordinates, which are exactly what is within the PTS format that you have. You can also use, let's say, this function to find the point distance between two different points. So you can click on one point and another point, and it will give you the distance there. Or for instance, from here to here, you can find where the distance could be. And the rotation there is pretty simple. You have to play around with it. You're going to get the hang of it, how to go up and down and how to rotate. I believe right click is rotation, and the middle of your scroller is going to, when you hit that and hold that, it's going to bring you up and down. And then here is basically where I want to also talk about the registration, because if you put both of these together, not only is that original model going to be larger because of the fact that when it came in, it came from inches and now it's in centimeters and meters, you now have to perform the rigid body transformation in order to transform these two coordinate systems together, as I explained there. Now, I've made your lives a little bit easier because I wanted you not to necessarily focus on creating your own registration, but to perform the registration the way that it is. So here I want to explain the registration there. If you go back, you go to edits, you go to apply transformation, and you click on the apply transformation. Now this is the so this is basically where you're going to be able to specify your orientation and your translation. So typically orientation, which you're moving it around, would be represented by this top 3x3 matrix here, this top 3x3 matrix. So right now is identity, meaning that whatever point is multiplied by this matrix is going to be the same point. That's what identity matrix is, which is a diagonal matrix where all of the diagonal elements is 1. If you want to rotate this only, you need to change just the top 3x3 matrix, where we call it a rotation matrix. And then for your translation, you need 1, 2, and 3 elements here. You don't really need to change anything about the last element there. That is only there so that you can use just one 4x4 matrix in order to multiply it to a particular point coordinates, which the point coordinate would be x, y, z, and 1 at the end, in order for it just to be nicer and cuter. But typically, you only have a 3x3 matrix times your xyz plus your translation. And this matrix would do the exact same thing. So if you see it's being divided versus this is just the algebraic summarization of the exact same matrix. There's no differences there. So the first 3 basically is where you change it. The last one, again, 1 is where you have your aspects there that you want to work with. For scale, you might want to scale this as well if you really need to, but for this, you don't need to scale because you've already resized the model properly, so you don't need to do anything with the point cloud. Now, what I've given you is essentially the transformation matrix. I've given you in the files there that you have most likely downloaded right now. You basically copy this into the same one, so it gives you the orientation, the translation, and everything alike. And then you click OK. Now these two are transformed. So I've basically made your life much easier than regularly. However, it's not that it's not possible. I just want it for consistency and for you to focus on the more important aspects rather than the registration. Still, there's some deviations between them, but that is basically the goal of the project as well, to be able to find those deviations and see if it's necessary to focus on that or not. So this is what you're going to be doing. For more of you enthusiasts that you actually want to do your transformation yourself or you want to play around with it, there's also an opportunity to perform this manually. So you have your point cloud. You basically, I would recommend to put it in orthographic projection because I'm going to explain later on. And then what you do is you use this function called translate and rotate. So the beauty of this is that you have tx, which is translation in the x direction, translation ty is a translation in the y direction, and tz is the transformation in the z direction. This does not have any orientation, meaning your model does not move or rotate. What it does is only translates. The second part up there is the rotation, which if you click on the rotation there, you're going to see XYZ, which is basically XYZ, which is basically your particular orientation overall. and then you can actually select a particular orientation and rotation axis. Meaning if you have the Z axis as your orientation, your model would only rotate about that axis. So right now what I've done is, for simplicity, and there was a reason why I did the orthographic, was so that we can check, for instance, how it would have to be rotated in the Z, how it would be rotated in the X and Y, and how much in the basically translation you need to go. So what I did was, right now, I focused it on Z, and I removed all of the translation. And now what I'm going to do is I'm going to take a look at the up here. So I'm going to have the top view. Now I'm going to rotate it, because the only one that is going to be working is the rotation about the Z. Then you can rotate it quite nicely. And then after that, because you're in the XY plane, you can now translate it in the X. And then wherever you're satisfied, you can stop. You can remove that. And then now you can only translate it in the Y. You can translate it in both of them if they're both checked, but it's better practice to do it separately, because then you don't have the problem. Now you have to translate it in the Z direction. So you grab the Z, the TZ, you now bring it up, and where you're satisfied, you can again scroll it and zoom in to see if you're satisfied. You need a bit more there or less. So you need a bit more. And then you also see that in the Y direction, for instance, you also need to move it, sorry, in the X direction. You also need to move it in this direction as much as possible. And then you could basically practice and play around with it. You need to maybe orientate it a bit more, the rest of it. But this is more or less how it would look like after, for instance, you play around with it manually. So it's not a very complicated process, but it most likely is not as accurate as the other one that I just put together. You can see some of these are actually left out. Some of these are a bit higher, lower. But if you're a bit advantageous, you want a bit more of an enthusiastic adventure, you can basically use this as well, and you can work with that. So this is basically the basic principle. What I'm expecting from you is to actually